So today we're going to be talking about surface micromachining, which is really more a MEMS type processing. We've been talking mainly about process modules and steps that people use, whether they're MEMS or whether they're CMOS. But once we finish with all that, we're going to start talking about real MEMS processing, meaning surface micromachining. But first, as usual, a couple announcements. So homework number 2 is due next Tuesday. I have no office hours tomorrow because we have the BSAC Industrial Advisory Board meeting going on. I figured out that on Thursday the schedule of the BSAC meeting is such that I actually can do the lecture on Thursday, except that I would have to do a lot of running around, which means I have to. So I'm giving a talk on Thursday. And if I do lecture on Thursday, that gives me 20 minutes to get back down to the Brower Center, which is down on Shattuck, to give my talk. A lot of people nervous about that. They don't want me to do it. So let me just ask this question. I have a room for next Thursday, or next Thursday. Remember, I'm going to be gone next Thursday too. So I do have a room for that finally. Whoops, no. I have a room on Friday. So next Thursday, I missed the lecture, right? And so I won't even be here on Thursday. But then the makeup lecture is going to be on Friday, the 30th, from 3:30 to 4:30 in 293 Corey. That's the room right next door to us. It has a laptop projector, but it does not have webcast capability. So I'm going to have to record it myself on my own local machine, and that works well when it works. If it doesn't work, then you're out of luck. Okay. I don't know how we fix that because I don't know how many people can make this Friday 3 to 4:30 time. And so I guess that's what I'm going to find out right now. How many of you can make 3 to 4:30 on Fridays to this lecture? Okay. How many cannot? Okay, so there's... You'll be late for half an hour. Is there another course or something? What if we moved it to 3:30 to 5? Then is it possible for everyone? No. Okay, there's still some people who can't make it. All right, so I guess I'm going to just have to make sure that the recording can work for that Friday. But I guess this week, let's do the lecture on Thursday. Okay, I may have to end it early. Right, so what we'll do is we'll start at 2. We'll probably finish 10 minutes early or something like that so I can get back and give my talk at the Brower Center, just to make sure I can get back there, because there's going to be a lot of nervous people if I'm not in the room 10 minutes before my talk. Yes?
That's still in this room?
Yeah, it'll still be in this room. It's just like usual, right? We'll have the usual lecture on Thursday. I'll be coming from there too, so I have to be there early in the day. There's some function that I'm to leave a little bit early, and I'll come to this lecture here. Hopefully I'll be here on time. We'll go from 2:10, whenever we usually start, till 3:20 or something like that. Okay, then I'll stop it at 3:20 because I have to head back down to the Brower Center to give the talk. But I guess it's always better if we could do the lecture during the prescribed time because then everyone can make it, so we'll do that. Okay, we will have our lecture this coming Thursday. We will not have lecture next Thursday. That I can do nothing about because I'm not even in town. And so lecture will be moved next week. The Thursday lecture will be moved to Friday, September 30th. Should it be 3 to 4:30 or 3:30 to 5? I actually have 3 to 5 reserved. 3:30 to 5? How many cannot make it 3:30 to 5? Cannot make it. That's the same number, right? If it was 3 to 4:30, how many cannot make it? Same. All right. Might as well make it 3 to 4:30 then. Oh, 4 to 5:30? Oh, okay. All right, so 3 is better. Starting at 3 is better, because you get at least 1 hour. Okay. All right, so this is what we'll do. And so we do have lecture this coming Thursday. Okay? Any questions about anything logically? All right, so let's hit the lecture. And so this is what we're doing today. We're going to finish process modules from Module 4. We're going to read, we're not going to read that. Every time I give you these outlines, right, I also give you the reading assignment. That's also on the syllabus online. so you know what you need to be reading in association with all of these lectures. So after finishing process modules, we then head into surface micromachining, which is, I guess, one of the more popular and one of the more successful methods for doing MEMS fabrication. There's a lot of products out there that use surface micromachining in high volume. And so we'll talk about a number of topics here. I guess all right. You can enjoy this for a minute here while I fix this thing. Okay, so we'll talk about surface micromachining in general, just the whole process flow, polysilicon surface micromachining. Then we'll talk about all sorts of issues that you have with the process. We'll touch upon these briefly here because we'll go back and cover them in a lot more detail later on in the class. And finally, we'll end up with some, I guess, almost foundry-like processes that you might have access to where you can start playing around with MEMS should you have the ability to do that, say, from your research. Okay, so I just said we were doing that. Okay, so let's head for this. Okay, where I want to go to the beginning. Okay, so we're talking about, well, we already talked about lithography. We're in the midst of talking about etching, and we're about to talk about doping. And we're going to finish all of this today. So last time we were here, we're talking about plasma etching and what it was. Well, actually, reactive ion etching and what it is. So we talked about plasma etching, and I think the takeaway from plasma etching is that when you do plasma etching, you are creating a plasma, but in this plasma, the things that actually do the etching are the neutral radicals. Okay, because we talked about how neutral radicals, they hate being neutral radicals, so they want to combine with something else to lower their energy state, which means they're very reactive. Okay, and in general, in any of these plasma processes, it's these neutral radicals that do the reaction. Okay, in reactive ion etching, however, like we said last time, because they're neutral radicals and they cannot be directed in any particular direction, they etch equally in all directions. So your generic plasma etch is an isotropic etch. It etches sideways and vertically exactly the same rate. Usually that's the case. And often because it's a gas, right? It can go in all directions without too much trouble. To make it more directional, which is what we like to have, so you'll see very soon that we like to have straight sidewalls, which you're seeing right here, which obviously you don't get with an isotropic etch. But to make it more directional, we now employ the ions in the plasma. In general, these are positive ions. And if they're positive ions, that means what you can do is you can put an electric field across this gap here and use that electric field to accelerate those ions into the surface of your film that you're trying to etch. And so by accelerating these ions, you can damage that surface. So we talked about ion milling actually doing etching. This is not as high a power as ion milling, but you're still directing these ions into the surface that of the film you're trying to etch. They're doing damage. They're not damaging it enough to blow off that film, but they're damaging it enough such that now these neutral radicals or other reactive species can come in and have a much lower activation energy for reaction. Okay, so they'll have a much faster constant for reaction, which means the reaction goes a lot faster in the vertical direction than it goes in the lateral direction. So without the damage in the lateral direction, there's still a little bit of reaction that goes on laterally, but it's much slower than the vertical direction. Okay, and so anisotropy is really a competition between lateral etching and vertical etching. You're always going to have some amount of lateral etching. However, if you can control it such that the selectivity in the vertical direction is much higher than that in the lateral direction, you get a vertical etch, and you get basically what we're looking for in a deep reactive ion, well, in a reactive ion etch. We'll talk about deep reactive ion etching in a second. Okay, so this is one mechanism for reactive ion etching, right? The damage mechanism. There's another mechanism, however, that can be used, and that is if you include among the gases in the plasma carbon type species, you actually can do things like grow polymers over your films. And so that's one other way to do reactive ion etching. So the way this works, you still have your radicals that are doing the reaction. You still have positive ions that you can direct into the surface to do damage. But this time what you're doing is not damaging the actual film. You're first growing a polymer over all surfaces, where on the sidewalls, that polymer covers the sidewalls and it prevents etching by the reactive species, by the neutral radicals. Okay, so now this neutral radical can go here and hit the sidewall, but it's not going to actually hit that film. It's going to hit a polymer material that it doesn't react with. Okay, so reaction is prevented on the sidewalls. It would also be prevented over the flat surfaces as well, except you're taking these ions and you're bombarding the polymer now and you're breaking up the polymer. Okay, so now you break up the polymer can no longer prevent reaction, and again you get reaction just in the vertical direction. Okay, so this is just the other mechanism. This is called the surface inhibitor mechanism, where you're using a polymer to advantage. You're still damaging something to allow etching in that direction to go faster, but this time you're damaging a polymer. Okay? So two different types of reactive ion etching. A very important one for MEMS application is what I mentioned briefly before. That's deep reactive ion etching. And so in technologies like CMOS and transistor technologies, a lot of the art of design in those technologies is to try to design them such that the layers you're etching are very thin. Right? And why do we want to do that? Because thinner layers means less topography, which means that your lithography can be much more accurate. Okay? So in CMOS, you want to keep everything as flat as possible. You'd like to do that in MEMS too, but often you can't because, you know, just the nature of it. There's a lot of 3D things that have very high aspect ratios. And so etchants for CMOS, they're usually tailored for very shallow etches. Okay, whereas for MEMS, people were researching methods for trying to get very deep etches. So etches that go all the way, you know, you can go through a whole wafer, for example, with some of these deep reactive ion etches. And the way that these things work is they're pretty much using the surface inhibitor mechanism, which means they're growing a polymer, but they're doing it again and again. So they have, you know, they're using inductively coupled plasma, which is a high density plasma, which means you can etch at a good rate. So the etch rate could be 1.5 to 4 microns per minute. But there's two main cycles in the etch now. You sort of do a cyclical etch. Okay, you may do an etch cycle where you're using SF6, which is something that etches silicon. So this is deep reactive ion etching of silicon here. That comes in and etches the silicon. You still have reactive ion etching. You're still using ions to sort of damage here to get more etch in the vertical direction than the lateral direction. However, you still get this lateral direction etch. And if you were trying to etch 50 microns down, you would probably cut in laterally many, many microns still. Not 50 microns, but probably more microns than you want. Right? And so what happens in this, you do this cycle for 5 to 15 seconds. Then you switch cycles. You completely change your gases to something carbon-containing, like this C245, that can deposit a protective fluorocarbon polymer over all the surfaces here. Okay? And so that's all you're doing during this 5 to 15 seconds. Then you go back to this cycle here. That is your reactive ion etch. So the ions are coming in. They bust out this polymer here, just like the surface inhibitor mechanism. They do another etch, but that etch, of course, is going to start bloating out sideways as well. But then you stop this, you coat this with a polymer, and you continue on down. Okay, and you can see this is a way that you can actually get some deep vertical etches with very little lateral etching going on here. Okay, you see the consequences of this, though. You end up with this scalloped sidewall. Okay, so the sidewall is not straight, it is scalloped. Okay, and a lot of people may not like that, but in MEMS, when your features are gigantic, right, these scallops can be 1 micron, 2 microns or something, but if your features are 50 microns deep, right, those scallops are probably going to be very small compared to all your different features there. Okay, and so here's some examples of what you can do with deep reactive ion etching. This is 20 microns, that scale there. So you can see that some of these things are really deep, about 60 microns deep or more here, with some very high aspect ratios. And you can see, though, that these with the very wide openings here, these got deeper than these with the very thin openings here. Okay, so why does that happen? That's because once you get very deep, it's just like any other process we've talked about, the reactants have to diffuse to the place where they react. And so when you have very thin openings, the diffusion is more difficult, so the reaction just goes slower there. Okay, do you have a question? Oh, I'm sorry. So silicon, so in these, I didn't even talk about these, did I? So the silicon dioxide, when it says 200 to 1, that means it's etching silicon 200 to 1 oxide. Okay, which means this etch doesn't attack oxide at all, almost. Okay, and we'll see that there's a consequence to that very soon when we start talking about MEMS. Yes?
Is there any way you can mask the bottom of the trench so that by not having the polymer where you can
So you're trying to get rid of the scallops, or what are you trying to do with that process?
reduce the aspect ratio? That's the goal. And so you eliminate the
Just here.
yeah.
So you mean there's some, but that's what's happening actually. When you switch to this cycle here, the ions come in and they blast off that polymer at the bottom. So in this cycle here, you would coat this part with a polymer. So you would come in and this part here would be coated with a polymer. That'll be coated with a polymer. This part would also be coated with a polymer, except these ions come in and they break up that polymer. Right? So they break up this polymer. So you already have something where you coat the edges with the polymer, then you come in and you break up that polymer there. Okay, there's many variants of this as well. And so you could take, I mean, in our lab, who makes these things? So STS makes these things, Plasmatherm. There's a bunch of different companies now that make these. The reactions are similar, but you can have different types of things. You can have things where actually the polymer can be etched away in some kind of chemistry instead of ions just breaking it up at the bottom. So what you're saying is possible too. There are chemistries that do that as well. But in the end, even this chemistry here will give you a very straight sidewall. So very high aspect ratios. All of them give you very high aspect ratios, but at the consequence of having these scallops. Okay, so like for example, in my research, I don't like these scallops because I rely on very flat surfaces between these to define a very specific capacitance. Okay? So sometimes you don't want the scallops. Now it's possible to get rid of these scallops by doing oxidation. So if you oxidize this, the oxidation will smooth out those sharp points. So you actually can do enough oxidations to get rid of those scallops to a good degree, to smoothen it out quite a bit. Okay? Yes?
I was going to ask just that.
Oh, how to smooth these things. Okay, yeah. So there's one good way to do it. There was another question. Yeah.
So the ions are highly directional, whereas the free radicals are kind of isotropic.
That's right. That's right. Yeah, the free radicals can go anywhere. And that's why you need this polymer here to prevent them from etching sideways. Okay? Yeah?
Are you etching the polymer in the following process? I mean, the polymer
Oh, yeah. So a lot of times you can get rid of these polymers at the very end of the process. So some of the processes actually get rid of them in process. So they're constantly getting rid of them, redepositing them, getting rid of them. But there's a chemistry that gets rid of the polymer as well. Okay, in these processes, you always can get rid of the polymer. Okay, that's a nice thing about these processes. So you'll find that there's polymers you don't know how to get rid of in other processes. But in this, when they're using the polymer, they're purposely using this polymer, they have a chemistry to get rid of the polymer as well. Okay? Yeah, so it doesn't stick around by the end of the process. Okay. And so we talked about this. So there's an etch rate variance depending on your mask. Okay, and that in general is going to be true. Right? So when we talk about, well, we've already talked about etching, but when we also talk about processing, that's why you never trust the etch rate that someone tells you for any particular tool, because that etch rate changes with the mask that you use. Right? The amount of material you have to etch will change the etch rate quite a bit. And you can see even here, just the sizes of the openings changes the etch rate. So this is not an unusual thing. This happens with almost everything. And that's why in the lab, if you're working in the lab, don't trust anyone's etch rate. Always determine it for yourself using your mask. Okay, so get a dummy wafer with a dummy layer of that film you want to etch. Use your mask on that dummy wafer and etch that dummy wafer for a certain amount of time, maybe 30 seconds. Measure the thickness before and after that etch, and there you determine your etch rate for that particular mask. If you use that etcher again, and you have a different mask, you got to determine the etch rate again. Right? Do not trust someone else's etch rate because it's going to be different from yours just because your mask is different. Okay? All right, so let's move on. So that's etching. So we're done with etching here. Let's move on to the next topic, which is semiconductor doping. Very important topic for transistor design, somewhat important for MEMS design. But as you'll see in MEMS, a lot of times we just don't care how much you dope it. We don't really keep great track of what the doping level is. We just want it doped and conductive. Okay? But before that, let's talk about doping of semiconductors. I know there are some MEs, some biologists, some chemies in this class who may not be as familiar with this as some of the EEs. Heck, some of the EEs may not be familiar with all of this if you're a system person of that sort. But semiconductors are not intrinsically conductive. To make them conductive, what we do is we replace the silicon atoms in the lattice with dopant atoms that have valence bands, so electron bands, with fewer or more electrons than the 4 of silicon. Right? So silicon has 4 electrons in its valence band, so its outer shell. And so what happens if we do this? So if we replace a silicon with an atom that has more electrons. So here's silicon. Each silicon atom has 4 electrons. And you can see that in this covalent bonding that you have between the silicons, right, if each silicon has 4 electrons, then if it bonds with 4 other silicon atoms, then they all have 8 effective electrons around them, which fills the valence band. Right? This is learning your chemistry, relearning your chemistry that you learned a long time ago and should still remember. Right? 8 is the magic number for a lot of different elements. If you get 8 around that, everyone is happy. Okay? So you take a happy silicon, and you now replace one of the silicons with, say, a phosphorus. And you look at the phosphorus, right? It's got 5 electrons in its valence band. If it's got 5 electrons in its valence band, it's still going to be happiest with all these silicons around it with 8 electrons around it, right? So sharing atoms, sharing enough electrons with silicon around it that it has 8 valence electrons. Well, what happens to that 5th electron in phosphorus? Well, now it's not really tied to the phosphorus, right? It's free to roam around this whole lattice. And can you think of something where you have a lot of free electrons, which is another material that has a lot of free electrons? Metals, yeah, that's all. I mean, what metals are, right, is they're a cloud of electrons free to move around that metal. That's why it's easy to pass current through the metal. That's why the metal is conductive. Well, if you think of it, by doping the silicon, you're basically making it a metal. Okay, you're creating a cloud of electrons that you can move back and forth with electric fields. These electrons are not really tied to these atoms. This is the simple hand-waving argument, right? If you're in a materials science class or other classes, you get much better arguments. But here, this is the best I'm going to do right here in the time that I have. Okay, so the larger number of donor atoms, which is what phosphorus is, you call it a donor atom because it donates an electron to the electron cloud here. The larger number of these atoms, the larger number of free electrons, the more it becomes like a metal, and so the more conductive it becomes. Okay, the higher the conductivity. Okay, this is the case for electrons. This is the case for doping with an atom that has more electrons than silicon. Now we have a conductivity equation where conductivity, which we played around with earlier in the class, is just equal to the electron mobility times the density of electrons. That's determined by the concentration of the dopants times the unit charge, so the magnitude of charge on a single electron. But you see I have another term here where I'm calling, instead of electrons, I'm calling them holes. Okay, so what the heck is a hole? Well, if you dope the silicon with boron, for example, which has 3 electrons, so 1 fewer than all its silicon counterparts, what that's going to do, boron's going to fit in here, but this is now going to look like it's a missing electron. Okay, and so what's going to happen, this is a missing electron that allows other electrons to go into this hole. Right? So you think of this electron going to that hole, well, that creates a hole right here. Okay, then another electron here goes into that hole, that creates a hole like here. So you can think of it as a hole moving, okay, in this direction here, where that hole now represents positive charge. Okay? So instead of thinking of this as an electron, we think of it as a hole, a missing electron. And that is just like positive charge. You put an electric field across it, it wants to go to the negative terminal of that electric field. Okay? So it's just the opposite of an electron. So lack of electron equals a hole. Effectively, you have a mobility associated with this as well. So this mobility, I mean, what is mobility? Mobility is not just how fast the electron can just rocket through all of these things. When the electron moves, or the hole moves, what's it really doing? It's really bouncing off of atoms, right? It's drifting from one point to another. Okay, and so that mobility is a measure of how much bouncing that electron has to do to get from one point to another under electric field. If your mobility is high, that means it doesn't suffer a lot of collisions as it goes across. If your mobility is low, it suffers a lot of collisions and takes a lot of field to get that electron across. You get very little current for the same amount of voltage. So I think you all know these examples, but right, transistors, they can have mobilities in the hundreds or so. Centimeter squared per volt second. And organic transistors, I suppose, where one, you're lucky if you have one. Okay, so lots of different things have different mobilities as well. So that's your doping 101, I suppose. And now let's start doing things with dopants, right? What we really want to do is answer the question, how do you introduce these dopants into different things, and how do you redistribute them? So one thing I want to talk about that is relevant to your homework is dopant redistribution during oxidation. Okay, so what do I mean by this? And so what I mean is that when you oxidize the surface of a wafer that has been doped, a silicon wafer that has been doped, you will move those dopants around just because you've oxidized the surface of the wafer. And how you move these dopants around depends on a number of properties of both the dopant and how it behaves in oxide and in silicon. Okay, so for during oxidation, the impurity concentration, that means impurity equals dopant here, at the silicon-silicon dioxide interface can increase, so it can pile up at that interface as the oxide grows, or it can deplete depending on the dopant type. And whether the dopant depletes or piles up depends on couple of things. One of them is the diffusion coefficient of that impurity in silicon dioxide. Okay? So once it gets into silicon dioxide, does it want to move fast at high temperature, or is it going to move very slowly even at that high temperature? Okay? Same diffusion coefficient that we've been talking about previously. I guess it is still the same for things like growing oxides and that sort of thing. There's also a segregation coefficient. So this is sort of a measure of the affinity of this dopant atom to either silicon or silicon dioxide. So the segregation coefficient M equals impurity equilibrium concentration in silicon divided by impurity equilibrium concentration in silicon dioxide. So what does that mean? Equilibrium concentration means that if this dopant was given a choice of what it wants to do, be an oxide or be in silicon, okay, where would it go? Where would it end up? So say you had a lot of dopants, and you had oxide on this side, silicon on this side, and you had all the dopants in the center, and then you said go, right? How many dopants end up in the oxide? How many end up in the silicon? That's sort of what this is, right? And the more that end up in the silicon, the higher this M is, the higher the segregation coefficient. Okay, so why is this important to know? Well, you could sort of predict after growing an oxide where the dopants are going to be, depending upon these two things, M and D. Segregation coefficient and diffusion coefficient. And so we could take a look at some examples. Take a look at boron. So what does boron like to do? Say you have a wafer that has boron in it. So it's been doped with boron. And you grow an oxide on this wafer. Okay, so what's going to happen as you grow the oxide on this wafer? Well, one, the oxide is going to grow, and it's going to grow into the wafer. Okay, so maybe I can draw that a little bit here. All right, so say I have a silicon wafer, but it's been doped p-type. So it's all uniformly p-type. And what I want to do is grow an oxide in this. That means there's p-type material even at the top here at the surface, right? So I grow an oxide on this. And you know that when oxide grows, some of it grows into the silicon, some of it grows out of the silicon. So there's my oxide. Okay, so as that oxide grows, what happens to the boron in this oxide? And how can I tell what's going to happen to the boron? I mean, what happens to the boron at the surface of the silicon? What happens to the boron at the oxide interface? Okay, so what I want to do is sort of plot concentration gradients here. Sort of like what I did for gases, but this time I want to, sort of do it like this. So this is oxide, that's silicon, and this is the oxide-silicon interface. And so when this whole problem began, what did I have? I had the silicon interface right here. Okay, so that's the original silicon interface right here. And I had boron doped uniformly throughout that silicon interface. So I guess for before I will use, where are all my nice colors? I'll use green. So that's the original boron concentration. Okay, I guess I should label my axes here. Call that X, which is the distance into the silicon. This axis here is concentration. In this case, of boron. Okay, so this is what I start out with. This is my starting thing. So now I grow this oxide, and that oxide moves this interface front to here. Okay, it also grows a little bit outside of the silicon. And now I want to know, okay, what happened to that boron here? As I grew that oxide, what happened to it? So I go back to this chart here and I take a look at boron. Okay, so this is the case for boron with no hydrogen present. Okay, there's another case with boron when you're doing oxidation with hydrogen present. Hydrogen present means you're doing a wet oxidation, right? Because remember, in wet oxidation, some of the byproducts are hydrogen. Okay, so that's with this second thing. But we're interested only in dry oxidation here. So if it's dry oxidation, I've got a very small m. Okay, what does that tell you? That tells you that the concentration in silicon, boron will have a very small concentration in silicon, a very large concentration in oxide, right? So as that oxide grows, those borons at the interface have a choice, oxide or silicon, right? If m is 0.3 or less than 0.3, that choice they're making is, okay, I want to be in the oxide. All right? So the boron wants to be in the oxide, but their diffusion constant is very slow in the oxide. Okay, once they get in the oxide, they can't go anywhere. They're stuck. All right, so what happens, what happens in this chart here, if I make that red, so after we do the oxidation, what happens is, okay, this boron now, right, all of it wanted to get into this oxide. Okay, and so that means it's depleted from the silicon surface. That means that the boron concentration at the silicon surface now looks like this. So this is after oxidation. Boron concentration. Deep into the silicon, it's still the same concentration as before, but up near the surface, you notice how it's been depleted. Okay, and then on top of this, right, once it gets in the oxide, it can't go anywhere. Right? So this boron is now all stuck in the oxide. So where the oxide, because there was no oxide before, right? But the type of oxide you grew now has a very large boron concentration in it like that. Okay, so in the oxide, this is your boron concentration after oxidation. And your concentration in the silicon after oxidation is now looking like this. And so what are you seeing here? You're seeing that the boron has been depleted from the surface of the silicon. Right, so in your homework problem, you have not only boron in your silicon, but you got some other dopants too. Okay, and those problems are there to sort of say, okay, so if this boron is depleting from the surface, doesn't that mean that it's possible that whatever other dopant I have in here, depending on what it does as that oxide grows, it can now dominate the doping concentration at the surface? The answer is yes, it can. And so that's what that homework problem is trying to get you to do, to figure out, if I had phosphorus and boron initially, but boron dominated, then I grew an oxide, what do I have at the surface? Is it still boron dominated, or did phosphorus come up and become the dominant dopant there? And if it did, then maybe I have a diode now at the surface instead of a conductive layer. Okay? So it's a very practical problem to understand. I guess going back to this, right, you have all these other cases. Boron, if you add hydrogen, still doesn't want to be in the silicon. It wants to be in the oxide, but its diffusion in silicon dioxide is very fast. Okay? And so that means instead of this, where we see a lot of we'll still see this where it depletes from the silicon surface. But instead of seeing a lot of boron concentration in the oxide, this is going to go away. And so actually the way that looks is right here. Okay, you see it depletes even more from the surface because not only is the boron depleting from the surface, its concentration in the oxide is very small here. So even more wants to head in the oxide there. Plus it's being pushed out of the oxide because it diffuses so fast in the oxide. Okay?
Where it diffuse back into silicon?
Out, no. Out of the oxide, yeah. So it's diffusing out of the oxide in this case, when you have hydrogen present. This is only when there's hydrogen present. Okay? And so on and so forth for the rest of these. See, phosphorus is very different, right? This has a very large segregation coefficient. This means it wants to stay in the silicon. It is a very small diffusion in oxide, so what happens with phosphorus is this. Barely any of it gets in the oxide, and when it gets in the oxide, it doesn't look like this. It looks like it's staying in the oxide, but it piles up at the silicon. So after an oxidation, the phosphorus concentration goes up near the surface, boron concentration goes down. Depending on the starting concentrations, you may have something very different in concentration than what you think you have after that oxidation. Okay, so this is just, I'm really just doing this to help you with that homework problem. And I think a little help with that homework problem too. Look at the scales of this. You're supposed to use these, okay? So if you look at the scale, right, that's 1 micron. That's X in microns. This is silicon. This is the same kind of plot that I plotted before. That's the oxide. This is the silicon there. Okay? So if you look at this, that's 0.2 microns. And the amount of oxide grown in the problem is 0.2 microns. Okay? That tells you can use these charts directly for that problem. Okay? It is a very simple problem. It's a very interesting problem to use. Okay? All right. So that's oxidation redistribution. Let's now move on to methods for introducing dopants into silicon in the first place. So with that problem, I said we already had oxide in the silicon. Let's now talk about methods to introduce them. And the first method is ion implantation. Okay, so ion implantation I'm going to go through very quickly because it's not that useful for MEMS. It's not that useful for MEMS because it damages things. Right? It damages materials, and you don't want to damage mechanical structure. And so here's what's happening. Ion implantation basically means you're taking an ion of the dopant that you want to implant with. Since it's an ion, it has a charge, you can give an electric field and accelerate it with very high energy into the silicon. You're basically just bombarding the silicon with this ion, and it's going to come in, it's going to push its way into the silicon, and most of them are going to end up at the average distance in, okay, which is called the range. But there's going to be some amount that end up in ranges around that average range, or distances around that average range. And that's really a standard deviation, something people call straggle in ion implantation land. So this shows the basic process. You have charged dopant accelerated to high energy by an E field. Possible energies could be 100 kiloelectron volts or something like that. You can control the current and the time to control the dose. Right? There are ions moving, so you can think of it as a current being sent into the substrate. You have some kind of masking material that doesn't let the ions through. And then you have the silicon where the ions get through, and the depth is determined by the energy that you give the ions and the type of ions they are, the type of dopant that you have. Okay, so obviously if you look at this more closely, the way that this really happens is how is that boron getting in there? Well, it's got to break bonds to get through, right? It's damaging that silicon. It's forcing its way through. And the way that it stops is it hits something, and the something that it hits, it's transferring energy to, which means it does some damage. Okay, so you damage a silicon layer, and initially, immediately after an ion implantation, you don't get what you're looking for, which is doping. You don't get a conductive semiconductor. you get something that's not conductive at all. Okay, and the reason for that is the boron, in order for it to be conductive, like we just discussed, it has to go in the lattice. Right? It has to go in the lattice so it can contribute its whole to the rest of the lattice there. And so the way that we put it in the lattice is after this damage is created, we do a high temperature anneal so that these borons can diffuse, and they're going to diffuse to a defect in the lattice, right, where there's no silicon. And so they're going to join that lattice by occupying that defect. Okay? And so you might ask the question, well, wait a minute, that silicon doesn't have many defects. Well, it does at high temperature. Or when you go to high temperature, you create defects in silicon. That creates opportunities for the boron to go into those defects. Okay, that's something you learn a lot more in 243. So in the end, the process is ion implant, high energy, then anneal. Once you've annealed, meaning go to high temperature, 800 to 1200 degrees C, now the boron is in the lattice, and it acts like a dopant. Your semiconductor is conductive. Okay? So pretty simple process. You can use the type of math that you all learned in your statistics courses, right? So it's a Gaussian distribution usually, and the equations for that I have written right here. I'm serious when I say I'm going through this very quickly, right? These are your equations right here. They're straight out of your statistics books, no different from them, right? You have R sub P, which is the average, right, called the range. Delta RP, that's the standard deviation, called the straggle as well. You can integrate this under there to get the complete amount of implant in the silicon, called the dose. And there's one-sided, two-sided forms of this. I'll let you look at those. We'll almost never use those things for implantation in this class. There are graphs, so in essence, it's not as simple as this Gaussian distribution is showing. There's actually the possibility to have a lucky ion. If you look down at the crystal lattice, you can have tunnels or so, right? Depending on what your surface is it 100, 111, that sort of thing. You could have tunnels where there's some ions that can go in and never hit anything for a long time, which means that this Gaussian curve may not be right. You may have to have this curve and then have a trailer in this curve that lasts longer. So maybe the curve, bad choice of color right there. Can I undo easily? No, I'm just going to have to use another color. Anyway, if I can, where is it? So something like that. That's a horrible curve that I just put in there. I can undo it, right? I can erase. Let's do that. Okay, so maybe it looks more like this. We have some that are lucky that you just get deeper. So not quite a Gaussian curve. And if you have that, there's people who've done theory, Lindhan, Scharf, and Schiott theory, LSS theory. They assume implantation into an amorphous material, actually. So they don't quite look at that lucky atom type thing. But using just amorphous material theory, you can get plots of projected range. So this is your average versus acceleration energy. And you can see that it's different for different types of implant ions. So there's boron, that's phosphorus with the bottom of the P missing there. But that is phosphorus, arsenic, antimony, different types of things that you can implant with. You also can get similar charts that give the straggle here. So that's like the standard deviation. And so when you do an ion implantation, you're using graphs like this. Usually you're using graphs like this and not a lot of the equations, just like we do oxidations, to figure out how deep you get a dopant into this. And so diffusion. Let's talk about diffusion. This is the way, so I'm done with ion implantation. See, I just wanted you to know about it, but really the way that you're going to do doping in MEMS is probably using a diffusion type process. So what is this? This is a ways for dopants to move in silicon. So you may introduce the dopant through ion implantation or another thing I'll talk about called predeposition, but you'll introduce it in a very shallow layer at the top of the silicon surface. And usually you want it a lot deeper than that. So to get it deeper, what you do is you take everything to a high temperature where the dopants now have a larger diffusivity, a larger diffusion constants where they can diffuse deeper into the silicon. Okay, so you're trying to make a much deeper amount of dopant into the silicon. And so there's three mechanisms by which dopants can move. And so one of them is a substitutional diffusion. This is where you have a vacancy in the lattice, and the dopant then just occupies that vacancy, then another vacancy opens up and it moves to that one, so on and so forth. And you may think to yourself, wait a minute, how can anything move like that? Silicon is a pretty pristine material. It's a perfect lattice almost with very few defects the way they make it. Well, no, not true when you take it up in temperature. Okay, when you take it up in temperature, those defects are there. More defects are there, so there's more opportunities for dopant atoms to move around in your silicon. Okay, there are other ways to move around in silicon too. There's an interstitial seed diffusion where the impurity atom replaces the silicon atom. Again, all of this made more possible at higher temperatures, right? Silicon can move out of the lattice location. The dopant can move in at the higher temperature. And finally, there's interstitial diffusion where the dopant doesn't even have to go into a silicon lattice point. It can just move outside of these atoms here. And that's the worst kind of diffusion if you're a CMOS type person, because that's where things like gold, right? That's why CMOS people are so afraid of people who play with gold and that sort, right? Because gold and some of these metals or some of these diffusers that don't have to get in the lattice, they just move around. So they can go great distances and cause you lots of trouble. Yes?
You talked about the temperature and
What's that?
the lattice vibrations also increase the temperature. And we have the mobility.
With mobility of the dopants? Well, mobility for carriers like electrons and holes will have a huge impact. Yeah, I mean, at higher temperature, right, that changes resistance. So that has an impact. But here we're talking about dopants moving around. So the dopants are not, they're not the carriers. They still move a lot slower than carriers do. They can't be moved around by field. Well, they can be moved around by field to some extent. So you take 243 for that. But all we're really saying is that at higher temperature, the number of defects in the silicon increases. And so the opportunity for a dopant to move around becomes greater. Okay, so you don't have to worry about the lattice vibrations. This is not a drift mechanism like carriers. This is just plain and simple diffusion. It's opportunistic diffusion is what it is. I don't know if I answered your question, but okay. All right. Okay, so diffusion in polycrystalline silicon. So we're talking about silicon, but in polycrystalline silicon, think of how diffusion happens. Okay, so there is that, you take it up in temperature and the dopants can move through the silicon, but in polycrystalline silicon, you have grain boundaries. Okay, and along the grain boundaries, the dopants can really move very, very fast. Right? So think of this, you have polycrystalline silicon, this is your dopant here, or your set of dopants. They move this way very fast, and then they can move into the silicon, into each of the crystals of silicon once they've gotten deep. This means that diffusion in polycrystalline silicon happens much faster than in silicon. Okay, so this is something you have to be careful with, right? A lot of people are used to doping silicon. We're going to talk about equations and formulas that predict how deep a dopant gets in silicon. But all that goes out the door when you talk about polysilicon, because in polysilicon it takes much less time at the same temperatures to get a dopant to go extremely deep into it. And in MEMS, a lot of times we're dealing with polysilicon. Okay, so let's now talk about the basic process for selective doping. And so usually in doping, what you do is you have some process that introduces the dopants. We talked about ion implantation. That's one way to introduce dopants. So I can implant my dopants into here. There's another thing called pre-deposition, where you basically surround the wafer with the dopants and they diffuse in a little bit initially. Okay? And then you take another step to drive the dopants in. So the second step is drive in of dopants. You drive them into the desired depth here. And you do that at high temperature, so greater than 900 degrees C in N2 usually, or in N2 with some oxygen. And you might want to do it in oxygen because you might want to grow an oxide over this first to prevent dopants from outgassing from the wafer. In fact, you pretty much always want to grow an oxide before you do a drive-in diffusion. Right? So that oxide can prevent diffusion of that dopant out of this system. Okay? So let's talk about this in detail here. In pre-deposition, a lot of times you use a furnace tube system, just like the furnaces that you use to do LPCVD depositions that we talked about. So you have a furnace where you're taking the wafers and you're sort of placing them in a boat where they're standing straight. So there's little slits in this boat and you put the wafer in the little slits, and it keeps the wafer standing straight. You use this to introduce a controlled amount of dopants and pre-deposition, but this kind of thing is not great in its control. So remember, dose equals the number of dopant atoms that you actually get into the silicon. And so using this furnace-based approach to introduce the dopants, you're going to have a range of from 10 to the 13th to the 10 to the 16th dopants per cubic centimeter is what I'm talking about here, plus or minus 20%. Okay, 20% is pretty bad, right? That means you don't have great control. And in CMOS, you don't like this at all. But in MEMS, you often simply don't care. Okay, so 20% is fine. And so as it turns out, this is one of the ways that people do it quite often in MEMS. Okay, for reference, just the comparison between this method, this furnace-based method, and ion implantation, which we just talked about. Ion implantation has a much larger range of doses, so it can go as low as 10 to the 11th. You can get up to 10 to the 16th. You can even get beyond that. But the accuracy is much better. You get plus or minus 1%. Okay? And you can get plus or minus 1% on the dose that you can get in silicon. So you can see the difference in accuracy. This is why in CMOS, people have used ion implantation to introduce dopants forever. Okay? Yes?
For the diffusion, dopant diffusion is
That's right.
for the ion implantation, it looks like I just need to
There's not a maximum. So this 10 to the 16th is not meant to be a maximum here. It's just it's a dose. First of all, this is not a. Yeah, did I say per cubic centimeter? It should not be per cubic. This is per square centimeter dose. It's per area is what this is. So these numbers you can't compare with dopant concentrations in silicon, right? But this 10 to the 16th is true. I mean, there's a solid solubility limit for the dopant in silicon. Right, and if you do drive in, you're limited by that limit. But in ion implantation, you're not. You can dope the heck out of it beyond the solid solubility limit. You're not going to get better performance than that limit, right? Because those dopants, in order to be effective, have to get into the lattice, right? They have to get together with the silicon in the lattice, right? But you can dope it heavier. You can put more dopants in there than the solid solubility limit, whereas you cannot with drive-in diffusion. Okay, you're right on that. So yeah, the important correction that I just said there. That's a per. These are in per square centimeter. So centimeter to the minus 2. Where when we do concentrations, it's centimeter to the minus 3. Okay? Yes? Never mind? Okay. Okay, so this is an example of boron pre-deposition. So you can see, you can put in a furnace, stand your wafers up, flow diborane and oxygen. And what this does in a carrier gas, some kind of inert gas, the temperature could be 800 to 1100 degrees C. What you do is you grow, what you're really doing is growing, this is why the oxygen is in there, you're growing a B2O3 glass on the surface of this wafer, and then at that high temperature the boron is seeping in from that glass into the wafer. Okay? It's difficult to control the dose because it's heavily dependent on the partial pressure of the B2 of the diborane gas flow. This is difficult to control itself, and so you get only 10% uniformity. And usually you have a situation where if this is your wafer, right, the gases are flowing around your wafer, they have to diffuse between wafers to the center. So what you do is you get a variation in doping concentration from the outside to the inside. Okay, there's where your 10% non-uniformity comes from there. Okay, a better way to do this is to use a solid source. So in this case, what you do is you're not relying on the gases to get in between those wafers. You're actually doing every other wafer, you're putting a boron nitride wafer in here, where it outgasses the boron into this. You still have reactions like this with diborane involved with oxygen. Same type of reaction, except this is more uniform because now your source of boron is right there where the wafers are. Okay, so you can get 2% uniformity across the wafer if you do it this style here. And so just general comments on pre-deposition. So higher doses only you can get. Ion implantation, which we just discussed, can go beyond even lower concentrations and higher concentrations. Ion implantation is also much better controlled. Uniformity for predeposition, not good, meaning diffusion drive-in, not very good. The maximum concentration possible, limited by this solid solubility limit. And there's different limits according to the temperature that you're at. So I'm putting about 10 to the 20th, but you need to look at a curve to figure out exactly what that number is. No limit for ion implantation. You're basically forcing it in there. And all of this adds up. This is why ion implantation is preferred for introducing dopants in semiconductor devices. Okay, but ion implantation is not necessarily the best choice for MEMS, and there's a number of reasons for that. One, say you have a beam that's already released that you want to dope the top and bottom side with. Can't do that with ion implantation. You only get the top side, right? With a gaseous diffusion, you can get the top and the bottom of that beam. Second one, ion implantation yields one-sided doping, right? So you're doping only the top side. And believe it or not, if you do that, if you do asymmetrical doping on a beam, so your beam, I guess I'll even draw that since it's important enough. So say your beam looks like this, and you actually dope it just at the top. Okay, what are you doing? You're introducing some stress at the top. So this thing wants to expand here more, which means this beam is going to bend. Okay, so that's your introduction to stress problems right there. If you have a stress gradient across a beam, that stress gradient is going to cause that beam to bend. Because where that stress gradient is, there's forces at the top that are pushing out. Those forces are not there at the bottom. And so those forces pushing out are going to force that beam to try to expand at the top, which means it's going to bend down. Okay, different dopants will make you bend different ways, but this is one reason why you don't want to ion implant your MEMS structures. You can get warping because it's not a symmetrical doping of this structure. Finally, also, ion implantation can do physical damage, and physical damage can affect your material properties. One of the things we'll be very interested in this class is quality factor, which means, we talked about those resonators, how sharp the resonant peak is. Well, you ion implant a material like silicon, you may damage it to the point where defects cause losses that lower your quality factor. Okay? And so for these reasons, ion implantation is not the best choice for MEMS. And for MEMS, people will use predeposition. And there's some pretty clever ways to do it too, as you'll soon see. But first, there's all sorts of modeling you can use for diffusion. As you suspect, I'm going to go through this very quickly. But the modeling just basically comes from the fact that everything wants to be at an equilibrium, right? It's almost universal. So if I have a doping profile that looks like this, so the N is doping concentration, that's doping concentration, X is distance. If my doping concentration is higher here than here, of course those dopants are going to want to go from here to there, so that in the end, in infinite time, this thing looks flat, right? You want to equilibrate everything. And that's really what Fick's law is, right? It's basically just saying that dopants from points of high concentration move to points of low concentration with a flux J. And Fick's first law says that that flux J is related to the concentration gradient by a constant, which is a diffusion coefficient. This is all very similar to the stuff we talked about when we talked about oxidation and LPCVD deposition. Another thing we have to worry about is a continuity equation for particle flux. This is basically saying that the rate of increase of concentration with time is equal to the negative of the diversion of particle flux. Okay, so this, I guess in a one-dimensional form, which is what we're interested in right now, which looks like this in one-dimensional form, so the derivative of the flux with respect to distance here. If you take this equation 2 and combine it with 1 from the previous, right here, you end up with Fick's second law of diffusion, which basically is a differential equation. Okay? And it's a differential equation you have solved in your past. You've taken math courses to do this. I'm sure you've done this in a physics course. So you know how to solve these things. You know the solutions depend on boundary conditions, so you have different solutions for different problems depending on what the boundaries are for these problems. You know the ways to do this, variable separation, Laplace transform techniques. There's a number of different ways to solve these differential equations. let's now start taking cases. So take specific cases which basically define the boundary conditions for solving this differential equation. Okay, so one case is predeposition. And so in predeposition, which we just talked about, that's where we have a constant source diffusion. Right? That's where we have a solid source between those two wafers, and that solid source is continuously supplying new dopants. Okay, what does that mean? That means that the surface concentration of dopants stays constant throughout the diffusion step. Right? Where the diffusion step, again, is taking it up in high temperature and doing that for a certain amount of time. Okay, so if I were to plot concentration versus distance versus time here, then initially you'll just have this concentration here, which is all flat. Not all flat, it's maybe a spike, a delta function of concentration there. But after a time t1 at a high temperature, these dopants move into the silicon, but the concentration at the surface doesn't change because you're continually supplying those dopants to the surface. Okay, that's the case we're talking about here. And as we go to other times, T2, T3, this moves out, and the concentration at the surface still stays the same because you're continually supplying that. That's what I mean by constant source diffusion. We're supplying the source of dopants at all times. Okay, it turns out that when you solve this equation, you end up with a complementary error function profile that's pretty much defined by this equation here. Sorry, this equation here, which you can also equate to what's called a complementary error function. And so that's ERFC is the abbreviation for that function. So it takes an argument, and there are tables and graphs. Your calculator, I'm sure, can calculate the complementary error function for you. For this case, right, because we had a boundary condition where the surface concentration stayed constant throughout the diffusion, that's how we solved the differential equation. We basically put in boundary conditions where n at x equals 0, the surface, at all times, is equal to n naught, which is a single concentration. And the concentration n at an infinite distance into the silicon at all times is always equal to 0. Okay, those were our two boundary conditions, and we used those boundary conditions to determine the equation that describes now these shapes here of concentration versus distance after a certain amount of time at a certain temperature. Okay, where the temperature comes into this d right here. So the temperature affects the d in that equation. Okay? I guess I'll just show, these plots here are log plots. Okay, so I'm plotting those on a log scale. This I'm plotting on a linear scale. Okay, so you may see it look like this, or look like those other functions that I showed you. You're just looking at the difference between log and linear, just for your information. Okay, in the end, right, you can also take this equation, you can integrate over infinite distance into the wafer. If you do that, you find Q, the dose, which you can put as a function of the time of diffusion that you do, T right here. And you can plot this, so on a linear scale, you can plot this dopant profile here. And what you'll end up here, this 2 times square root dt ends up being a characteristic, divided by square root pi, I should say there, ends up being a characteristic diffusion length that is equal to the length or the depth at which you have a box that has exactly the same concentration as what you would get if you integrated, exactly the same dose, number of dopants, as what you would get if you integrated infinitely into that silicon. Okay? So it's just kind of a characteristic length. You see these all over the place in semiconductor physics, right? Okay, there's the other case, drive-in diffusion. So in drive-in diffusion, you're no longer supplying your source. Okay, so you supplied your source, which means you did a predeposition. But in drive-in, what you do is you now cover the surface of the wafer with an oxide, and then you take it up in temperature. And because you covered it as an oxide, none of these dopants are going to diffuse in that direction. They're all going to diffuse inward towards the wafer. And now your diffusion profiles with time look like this, where now the surface concentration is no longer constant, right? Because you're taking dopants and moving them into the silicon. Surface concentration decreases with time. Whoops. Decreases with time there. You have new boundary conditions. Your boundary conditions are still that in an infinite distance into the silicon, your dopant concentration should be 0. But another boundary condition now is that the derivative of the dopant concentration with respect to x, the gradient at the surface, exactly at the surface, has to be 0. Why? Because we're saying it's constant dose. We're saying that we're not losing any dopant flux out of that wafer. Okay? So that's equivalent to what that's saying. Plug these boundary conditions into that differential equation, and you get a Gaussian distribution now. And this equation that I'm writing here actually corresponds to a half Gaussian. And if you did an ion implantation, for example, where your dopants were deep into the wafer, this equation would correspond to this half here, where you would substitute in for Q this di over 2, where di is the dose of the implantation. Okay? So I'm doing this fairly quickly with some assumption that you know this. I know some of you already know this because I've spoke to you in office hours, but there's some who don't. If you don't, if I'm going too fast, all of this is in that Jaeger text. You can read it fairly quickly, and I think this stuff is just more easily understandable than a lot of other technical stuff in engineering. So in the end, our diffusion procedure is a two-step process. So we have a pre-deposition, which is a constant source diffusion. We have a drive-in diffusion after this, which is a limited source diffusion. And so the question becomes, okay, for constant source diffusion, we found that the profile of the dopants was a complementary error function. For drive-in diffusion, which is limited source diffusion, we found that the profile is a Gaussian distribution. So if I'm given a process where I did pre-deposition for a certain amount of time at a certain temperature, then I did drive-in for a certain amount of time at a certain temperature, what is my final profile going to look like? Is it going to be Gaussian? Is it going to be complementary error function? Or is it going to be some combination of both? Okay, the answer is that usually one of them has a much larger dT product, which is diffusion constant times the time at high temperature, than the other one. And the one that has the higher dT product is the one that wins. Okay, so in other words, if the dT of the pre-deposition was greater than the dT of the drive-in, then just assume that the profile of your dopants is complementary error function. Vice versa, if the drive-in was more than the pre-deposition, assume the impurity profile is Gaussian. This is usually going to be the case, because usually what you do is you do a short step to introduce dopants in, and then you drive it in for a long time to get it to a certain depth. Okay, so the second step is usually going to be the case. For actual processes, the diffusion, there's many high temperature steps that come in. It's not just a matter of, okay, this is a D that corresponds to one temperature, this T corresponds to one diffusion. Usually in a process, you have many steps where there's high temperature. Okay, and so in the end, you're going to have many dT time constants for each of those steps. And so for example, typical overall process, you do some selective doping. Could be an implantation. Okay, in an implantation, this is kind of important to know, the effective dT, you can define an effective dT, which you can pull right out of the Gaussian equation that I had in a previous slide. That's equal to delta RP squared divided by 2. So the standard deviation squared divided by 2. For any implantation, if you know the standard deviation, you know its effective dT constant. Okay? Now, if you did drive-in or activation, you know that dT constant because you know the temperature at which you did the drive-in. And I think I want to write that down. Right? This is a function of temperature, T. Okay? So that's where temperature comes into this. That comes in the diffusion coefficient. And then T is time. Okay? And then you have all sorts of other high temperature steps. So suppose in the beginning of your process you did an implantation. Then you did a drive-in. Okay, that's DT1, that's DT2. Okay, but then you came in and you did an oxidation. Maybe you did a reflow for PSG at a high temperature. Maybe you did a deposition that was a sufficiently high temperature. Right? All of these introduce temperatures, which introduce a diffusion coefficient associated with that temperature. All of these took a certain amount of time, which introduces a T. So all of these steps introduces a different additional dT constant to all of this. Okay? And so to determine, you see each has its own dT product. And so to determine what the final profile is, determine which had the largest sum of dT products, whether it's Gaussian or complementary error function, and then just use that sum of all the dT products in that distribution. Usually it's going to be the Gaussian distribution function. Okay? Does that make sense to everyone? I'm doing this very quickly. And so if you had this before, I could see people who've had it before, they're nodding yes. Those who have not may not be nodding. But this is something you'll have to read through, and actually doing some of the problems in the homework will help out too in the understanding. This is a chart that gives what this diffusion coefficient is made of. It has an Arrhenius dependence. So you can see that temperature dependence right there. And it also has some D0 constant, like all these other diffusion constants that you've looked at. Okay, just like the oxidation one, but different values here. So there are graphs of diffusion coefficients as well at different temperatures. So you could see substitutional interstitial C diffusers. These have reasonable diffusion coefficients on the order of 10 to the minus 12, 10 to the minus 13, 10 to the minus 11. You could see gallium, boron, phosphorus, arsenic in there. Then you can go on this side and look at the interstitial diffusers. So things like gold, copper, lithium, iron. This is why CMOS people don't like them, because it doesn't take a lot. Right? Look at their diffusion, 10 to the minus 6 compared to 10 to the minus 12. Right? We're talking 6 orders of magnitude faster diffusion. So if you get gold anywhere near your CMOS circuit, right, that gold is going to find its way to your devices. And it's going to take very little time and very little temperature for it to do that. And that's why any CMOS process person has to live in utter fear of any gold anywhere around their devices. Okay, so that's why we have these rules in the microlab that there's no gold allowed in any of these tools that have to do with CMOS. Okay, what do we do with all this diffusion? Well, we're interested in creating junctions that have certain depths. So there's a certain thing called metallurgical junction depth, X of J. And what this is just the point, if you have two different types of dopants, so maybe this is P-type and this is N-type, this is the point at which the two dopants have the same concentration, so cancel one another. And you can think of that as a junction, a boundary between the P-type dopant and the N-type dopant. Okay, so if these are the actual dopant concentrations, you have an N-type background, this is your P-type diffused or implanted concentration. Then the actual concentration, which is going to be N of X minus the background concentration, looks like this. Okay, where this is your junction, and X of J, this distance here, is your junction depth. Okay, so how do you determine junction depth? Well, that's very easy, right? So you just take these equations that we just derived for diffusion that give us our diffusion profiles, and then you just equate them to the background concentration, which you can see we usually assume to be a constant concentration, but that's not always the case. It could vary too. But you equate it to the background concentration at X of J, okay, and then you solve for X of J for each of these cases. And so there's some very simple equations here that tell you what junction depth is as a function of your doping profiles. Sheet resistance. We sort of talked about this before when we talked about scaling. But I'll go through it again. So sheet resistance is basically just your conductivity, which is 1 over conductivity is resistivity, which is this rho here. And so to get resistance, you take rho times length divided by area. Before we had L divided by sigma divided by area. This is the same equation, except talk about sheet resistance. What you do is you become a little bit clever and you say, okay, if I have a constant thickness of this dopant within my silicon or constant thickness of a conductor or so, then I can pull out resistivity rho and thickness T and call that one parameter here. We call that my sheet resistance. And now that sheet resistance multiplies by L divided by W. But what's L divided by W? Well, here's my block. There's L, there's W. L divided by W is a number of squares I can count on the surface of that block. Okay, so this is where people suddenly come up with this thing of sheet resistance where they give it a unit in ohms per square. Okay, so when you see ohms per square, that's what they're talking about. They want you to take the surface of whatever material that is and divide it up into squares and take that number and multiply it by whatever RS is in ohms per square. So in this case, I could see 5 squares here. The resistance is going to be sheet resistance RS times 5. Okay? Now, in general, you don't have a trace that is like a box, that has a cross-section of a box, right? In general, your cross-section is going to have some curvature there. And you're not going to have a uniform dopant concentration from the top to the bottom, right? It'll be non-uniform there. And so in that case, all right, so hold that thought. Let me first talk about this right now, and just to tell you that, how many squares is this run right here? So you could think of this as some interconnect here, but how many squares do I really have there? Well, all right, I got one square here. I got another square there. All right, imagine those are the same size. Okay, I have some more squares coming out here, right? But then I got a square right there. How much of a square is that? Right? You could say, oh, that's a square. What's the problem? No, it's actually not a square, right? Because you take any of these other squares, right? The current has to go that distance. Current goes that distance. All the current goes through the same distance in this square. But in this square, boy, this current only has to go that far. Okay, and that current only has to go that far. Okay, so in actuality, the number of squares in a corner is smaller, right, than a single square. And so you can do all these analyses here to figure out, how many squares this is equal to. And it turns out this corner is 0.56 squares. If you have a situation where this is a conductive, right, this is a metal here, or let's say sigma equals infinity, in this part right here. If you have something there, we have an infinitely conductive part here, then what's the current going to do? The current's going to go here. Some of the current's going to do that, like that, right? The current's not just going to take a path all the way through that square. So again, if you have a conductor in the middle of this, the equivalent number of squares for this is going to be smaller than one square. And then ends up being 0.65 squares as well. Well, not as well, but 0.65 squares. Okay? So we may have a homework problem in your future that makes you determine exactly how many squares certain features are to determine resistance here. Yes?
So what's the center there with the X that's, non-conductive? Okay.
No, this is a conductor.
Oh, okay.
Conductivity is infinite.
Okay.
So it's a perfect conductor.
So 0.665 square.
That's right. So what's happening, right? So this is one square, right? Yeah. Obviously that's one square. If I didn't have that conductor in there, what path would the current have to take? The current would have to take this path, that path, right? I mean, it would take this path, right? Yeah. Now, with this conductor, the current doesn't take that path, right? Some of the current takes an even longer path that does that, right? But some of the current takes a much shorter path that does that, right? And because of that, this is no longer one square. And so how do you work these problems? Well, you kind of divide them into more squares, right? So to work this problem, for example, at the top right corner, I would do the following. I would divide this into smaller squares, like that. Okay, and then I would say, okay, this current takes only one square path. This current here takes 3 squares, and so on and so forth, right? And each of these now represents a resistor, and resistors in parallel, right? You can sort of put resistors in parallel together. That's how you arrive at that 0.56, right? In the infinite, as these squares become infinitely small, you will arrive at 0.56 squares. Okay? So that's how to visualize doing one of these problems, and we'll probably give you one of these problems in the near future. Okay, so finally on this, and I guess I'm already running out of time, so I won't get to surface micromachining today. But finally on this, well, that's what I was talking about in the slide before, right? You don't have a cross-section that looks like this, right? It's not a perfect rectangle. You have a cross-section that looks like this. And in actuality, the concentration gets smaller as you go deeper into the silicon, right? So it's not something where you can get sheet resistance by just calculating depth and multiplying by a uniform conductivity. You have a different conductivity at a different depths within the silicon. And so you have to integrate along this axis here. Which in this case is x, right? And that point right there is x of j. Okay? And so to do this right, you have to integrate in order to get this sheet resistance. It turns out that someone has done this already. Irvin has done this. And so as with most of other things we've talked about, we have some theory for it, but you can easily just determine things just using graphs. Right? And so this graph is a graph of, and you may not be able to see all of this here, but this is surface concentration. This is the concentration at the surface of the wafer. And so if I were to draw this, so that's x, that's n. So there's n naught, which is the surface concentration, right there, plotted along the x-axis. and the y-axis. And then along the x-axis, you have the sheet resistance times x of j. So you know that's going to be x of j. Well, that's a j. That point right there is x of j. Okay? And then you want to know the sheet resistance in the end. And all of these curves are plotted with respect to background concentration. So that's n sub b. So all of these things are there, right? That's background concentration. X of j is in this formula here. And you're usually looking for r sub s. Okay? So you know how to do this, right? Usually you're given your surface concentration, you're given your background concentration, you're given the type of concentration gradient there is, and maybe you're given the junction depth. And when you're given all three of these things, you can sort of find them on the axes, plot out this point, pull down here, get this RS times XJ, right, and then solve for RS, and that's your sheet resistance, right? Or you can go back and do this integral, which I wouldn't do if I were you if these curves exist, right? There's curves for everything. So these are curves for n-type diffusion, both complementary error function and Gaussian, and here's p-type, complementary error function and Gaussian. Okay, so that's it for diffusion, and I guess I am out of time, so we'll end it here and start surface micromachining in the next lecture, which will be this Thursday. So if you came in late, I announce we do have lecture on Thursday this week. I will not miss lecture on Thursday this week. I'll miss lecture Thursday next week. Okay?